Welcome back. In the previous video, we've already seen that when the dependent variable is binary, the arrow term is heteroscedastic. In this video, we will formally learn how to deal with heteroscedasticity in OLS regression. Clearly, if there is heteroscedasticity, Assumption 5 of the multiple linear regression model on the constant variance of the arrow term does not hold anymore. The conditional variance of the arrow term will be different for different values of the independent variable x. What are the consequences of heteroscedasticity? First, we will still obtain the unbiased estimators from OLS regression. The unbiasedness property of OLS estimator is mainly depends on the conditional zero mean assumption. Also notice that the R square will be unchanged because R square is 1 minus SSR divided by SST. The denominator depends on the observation of y, and the SSR, as long as the OLS estimators are unbiased, the residuals UI hat is also unbiased for the arrow term UI. However, when we derive the variance for the estimator, variance beta hat, we need to apply the variance of the arrow term. With heteroscedasticity, the estimator for the variance is biased. A more serious consequence is that we cannot use the standard statistics to perform hypothesis test. The t-statistic is equal to beta j hat minus 0 divided by the standard error of beta j hat, and this standard error is the square root of the variance of beta j hat. With heteroscedasticity, the t-statistic does not follow a t-distribution anymore. Other inferences based on p-value or the confidence intervals also depend on the t-distribution. Therefore, we cannot use them either. In this lecture, we will learn how can we modify the usual OLS test statistics in the presence of heteroscedasticity. First, let's consider the simple linear regression model with only one independent variable, xi. The assumptions 1 to 4 still hold. We do not impose the assumption 5 on the constant for the variance of the unobserved factors. Instead, now we assume that the variance of unobserved arrow ui is now equal to sigma I square. Remember that when we introduce the homoscedasticity, we say that the variance covariance matrix of the arrow term is in this form. The diagonals are all sigma square. This means the variance of the UI conditional on x is always sigma square. But given this specification for the variance for the arrow term, now the variance covariance matrix is sigma 1 square, sigma 2 square, until sigma n square. We do not require that sigma I square equal to the sigma j square. Therefore, we have heteroscedasticity because conditional on different values of the xi, the sigma squares are different. Given this new specification for the variance of the arrow term, now we can similarly derive the variance of beta 1 hat. We first simplify the formula for beta 1 hat, which is equal to the sum of xi minus x bar yi divided by the sum of xi minus x bar square. And if we replace this yi into the formula, we will have this term. Knowing the variance of the arrow term ui, we can also calculate the variance of beta 1 hat. It is equal to summation xi minus x bar square summation xi minus x bar square sigma I square. So the population variance for beta 1 hat under heteroscedasticity is this term. Remember that under homoscedasticity, the variance of beta 1 hat is equal to sigma square divided by SSTX. When sigma I equal to sigma for all I, it means we do not have heteroscedasticity anymore. Then this formula variance of beta 1 hat will exactly equal to the variance of beta 1 hat under homoscedasticity. Recall that this sigma square is often unknown for the population model, so we often use the residuals to estimate the population variance of beta 1 hat, which we use beta hat square. The variance hat of beta 1 hat is equal to SSR divided by the degree of freedom divided by the SST of X. Now with heteroscedasticity, we also need a sample version to estimate this population variance of beta 1 hat. White proposed an estimate for this population variance to correct heteroscedasticity in 1980. If I remember correctly, this paper is the most cited paper in economics. The estimator, which is variance beta 1 hat is equal to this term. We still have the SST for the denominator, but for the numerator, we replace the sigma I square with the ui square. Here I will skip the formal proof to show why it is a good estimate for the population variance for beta 1 hat. It requires the law of large numbers and asymptotic property of OLS estimators. But we can treat it as an adjustment on the weight on the residual squares. Compared to the homoscedasticity case, the variance of beta 1 hat under heteroscedasticity can be written as the SSTX and take the sum of SSTX xi minus x bar square times the sigma I square, which is equal to SSTX summation of weight I sigma I square. If we compare these two variances, we kind of reweighting the sigma I square under heteroscedasticity. So similarly, to estimate this beta 1 hat, we also need to reweight the residual squares. Also notice that this formula is valid estimator for beta 1 hat of any form. It's just when the arrow term is homoscedastic, the variance will degenerate to the sigma hat square divided by the SSTX. The square root of this estimate is called the heteroscedasticity robust standard error, or simply robust standard error. Once we have this robust standard error, we can similarly construct t-statistics or other inference tools to perform hypothesis test. If the robust standard error is also valid for homoscedasticity case, and it is more often to have heteroscedasticity in practice, you may be asking, why bother with homoscedastic standard errors? The answer depends whether we can or cannot have an exact distribution for the t-statistics constructed based on the robust standard errors. If homoscedasticity assumption holds and all error terms are normally distributed, we've learned before that the t-statistics have the exact t-distribution, regardless of the sample size. But we obtain heteroscedasticity robust standard errors based on the law of large numbers and asymptotic properties of OLS estimators. It means they are only valid as sample sizes becomes large. If the sample is very small, the robust t-statistic can have distributions that are not very close to the true t-distribution for the estimator. And we may have incredible inferences based on these t-statistics. In R, we can use the function coefficient test to get the robust standard errors for the OLS model. The robust standard errors may be larger or smaller than the OLS standard errors. It means it can make the t-statistics larger or smaller compared to the OLS one. Then it will change whether a coefficient is significant or not. So one lesson from here is that whether or not we use robust standard errors should depend on whether we find heteroscedasticity or not. It should not depend on which one gives us more significant results. Here is an example for the relationship between education and earnings. Each point is an observation. From this fitted line from the OLS regression, we can see that the education is positively associated with earnings. But for people with high education levels, some of the earnings are very low, but also many of them, their earnings are quite high. For these types of observations, we often suspect that there is heteroscedasticity. A more direct way is to check the residuals from the OLS regression. By the nature of OLS residuals, the summation of all residuals is still equal to 0, but for high levels of education, the residual squares are much larger than the low level of educations. If we still assume that the error terms follow the normal distribution, then for low level of education, the normal distribution could look like this. But for high level of education, the normal distribution are more spread. It means the conditional variance for the error term sigma I square differs for different xi. As we showed for the binary dependent variables, it is quite easy to correct heteroscedasticity in OLS regressions in R. First, we run the standard OLS regression to get the homoscedasticity consistent standard errors. Then in the second step, we use the function coefficient test for the OLS regression. This function will follow the formula we derived before and give us the heteroscedasticity consistent standard errors. Again, the coefficients are the same before or after the robust standard error adjustment, but the standard errors now are robust, so the t-values and p-values that calculated based on the standard errors are now also different. To do hypothesis test, we need to rely on the robust t-values or the robust p-values. We can also calculate the standard errors by hand, either it is heteroscedastic or homoscedastic. If we apply the function variance-covariance HC for the regression model, it will give us the variance-covariance matrix for two coefficients, beta 0 hat and beta 1 hat. What we are interested are the diagonal elements. The first gives us the sample variance for beta 0 hat, and the second is the sample variance for beta 1 hat. If we take the square root of the diagonal elements, we will have the standard errors for beta 0 hat and beta 1 hat. Here we apply the white heteroscedasticity consistent robust standard errors, so this gives us the robust SE. Following the same procedure, if the method is constant, it will give us the standard errors, which is the same as we get from the OLS regression. It is not always better to use the robust standard errors. We should only consider it when there are indeed heteroscedasticity. How to identify there is heteroscedasticity for the error terms? One simple identification approach is through the visualization of the data. It can be the plots between x and y, or the plots between the x, the independent variable, and the residuals from the OLS under homoscedasticity assumption. Another approach to identify heteroscedasticity is to implement tests in R. For instance, we can use the command BP test to conduct a Brauch-Pagan test. Here is the command and the results. We simply use the BP test for the OLS model. Then according to the p-value, it is very small, so we can reject the null hypothesis that the error terms are homoscedasticity. Therefore, it is justified to correct for the heteroscedasticity and use the robust standard errors. Once we have these robust standard errors, then we can calculate the robust t-statistics and to do the hypothesis regarding the true parameter beta j.